All right, today we are diving into a really special piece of engineering, the synchronous motor. Now, this is not your everyday electric motor. Oh no, this one's a specialist, and it's famous for one incredible, almost unbelievable characteristic that just sets it completely apart from the rest. Let's get into it. Just think about that for a second. What if you had a motor that you could load up and then load up some more and its speed wouldn't budge, not by a single RPM? I mean, it sounds kind of impossible, right? But that is the entire premise of the synchronous motor. It either runs at one single perfect speed or it doesn't run at all. So how on earth does it pull off this magic trick? Well, to really get it, we need to break down its three defining features. First, like we said, it's all or nothing. It runs at one constant, synchronous speed. Second, and this is a big clue about how it works, it can't actually start by itself. And third, it has this kind of electrical superpower. It can actually control its power factor, which, believe me, is a huge deal in big industrial settings. And these things aren't just some novelty you'd find in a lab. You see these motors in really heavy-duty industrial applications. We're talking huge compressors, massive fans, generators, basically anywhere that keeping a precise, constant speed is absolutely critical. They are the workhorses of perfect timing. So, let's get to the heart of it. How is this perfect speed even possible? Well, it all comes down to one core concept, and it's called the magnetic lock. So, the first piece of the puzzle is the stator. That's the stationary outer part of the motor. Now, when you feed it a three-phase AC power supply, which is super common in industry, it generates a magnetic field. But here's the cool part. This field isn't static. It actually rotates around the inside of the stator at a perfectly constant speed. And we call that speed the synchronous speed. Now, this right here is exactly why the motor can't start on its own. Imagine the rotor, the inner part that's supposed to spin, is just sitting still. As that magnetic field from the stator sweeps past it, it first pushes the rotor's magnetic poles away, and then, a split second later, it pulls them in. This push-pull happens so incredibly fast that the poor rotor, with all its inertia, just kind of sits there and vibrates. It never gets a consistent push in one direction to get going. But, and here's the breakthrough, what if we give the rotor a little help? What if we can get it spinning up to, or at least very close to, that same synchronous speed? Well, that's when something amazing happens. The north pole on the rotor gets captured by the passing south pole of the stator's field, and the rotor's south pole gets grabbed by the stator's north pole. They literally lock together, just like two powerful magnets snapping into place. And that is the magnetic lock. It's this powerful, invisible connection between the rotor and that rotating field of the stator. Once that lock is engaged, the rotor has no choice. It is magnetically forced to spin at the exact same speed as the field. Not a little slower, not a bit faster. It's in perfect synchronicity. Okay, so we've got this incredible magnetic lock, but it also creates a couple of very practical challenges. First, how do we even get it started to achieve that lock in the first place? And second, what in the world happens when we put a load on it? Does that lock just break? The starting problem is pretty straightforward, really. Since the motor can't start itself, it just needs a helper. Think of it like giving a car a push start. Often, another small motor or a special winding is used to spin that rotor up to near synchronous speed. Only then is the rotor's own electromagnet energized, allowing that magnetic lock to finally snap right into place. Okay, so this is the really big question. If the speed is truly, unshakably constant, what gives when you attach a heavy mechanical load? Does the motor just give up and stop, or does something else entirely happen? The answer is just fascinating. The speed doesn't change. Not at all. Instead, the rotor's physical position actually falls back slightly compared to the rotating magnetic field that's pulling it. This angle of lag has a name. It's called the load angle. So as the load gets heavier, that angle gets bigger, but as long as the lock holds on, the speed remains perfectly, absolutely synchronous. Now, to really help make sense of this, there's a fantastic analogy from our source material that compares this whole electrical thing to a really simple mechanical system. I want you to picture two pulleys connected by a flexible, kind of twisty rubber shaft. The pulley that's doing the driving, that's our stator's field. And the pulley that's being driven, that's our rotor. Now, when you put a load on that second pulley, what happens? The rubber shaft twists, right? The driven pulley falls back by a certain angle relative to the driver. But here's the key. They both still complete a full rotation in the exact same amount of time. That twist in the shaft, that is exactly like the load angle in the motor. All right, now for the motor's other really unique trick.
Beyond its constant speed, it can actually influence the entire electrical system that it's connected to. And it does this by controlling the DC power, or what we call excitation, that's supplied to the rotor's electromagnet.
So, by adjusting the strength of the rotor's magnetic field, you can completely change how the motor behaves on the power grid. If you underexcite it, give it less DC power, it draws a lagging current, kind of like a standard induction motor. But if you overexcite it, give it more DC power, something really special happens. It starts to draw a leading current.
The easiest way to think about it is like this. Electricity has a rhythm between its voltage and its current. With underexcitation, the current's rhythm falls behind the voltage, it lags. But with overexcitation, the motor actually pushes the current's rhythm ahead of the voltage, it leads. And this ability, the ability to generate a leading power factor, well, that's its superpower.
So why does this even matter? Well, a lot of industrial plants are just full of motors that create a lagging power factor, and that's really inefficient for the power grid. So you can install a synchronous motor to do its mechanical job, whatever that is, and at the same time, you can overexcite it so it runs with a leading power factor. It effectively cancels out all the lag from the other equipment, making the entire factory way more efficient. It's a 2-for-1 deal.
Okay, finally, let's wrap this up by looking at the practical limits of the motor. You have to understand its different torques to know how to use it right. Think of these as the rules of engagement.
So there are 4 key torques you gotta know. First is starting torque. That's the initial grunt needed just to get the thing moving. Then there's running torque, which is what's needed to handle the steady, day-to-day load. Pull-in torque is how strongly the motor can latch into that magnetic lock. And finally, the big one, pull-out torque. This is the absolute maximum load the motor can handle before that magnetic lock breaks and the whole thing just stalls out.
So, if you're going to take away just 3 things from all this, let them be these. Number 1, a synchronous motor is a unique machine that runs at a perfectly constant speed, period. Number 2, it pulls off this amazing feat using a powerful magnetic lock between its rotor and stator. And number 3, its industrial superpower is the ability to control its power factor to make the whole electrical system better.
And that kind of leaves us with a final thought, doesn't it? The synchronous motor is this marvel of engineering, designed for absolute perfect timing. It really makes you wonder, in our increasingly complex and interconnected world, where else does this kind of precise, unwavering synchronicity play a critical role in powering our daily lives?